Hello students, in this video we'll study how to solve second order homogeneous constant coefficient ordinary differential equations. A homogeneous second order constant coefficient ODE has the form AY double prime plus BY prime plus CY equals 0, where here A, B, and C are constants. What we'll do to solve this ODE is to symbolically introduce differential operators. Let D denote d by dx. So we use capital D to denote a derivative and rewrite the ODE as a d squared y plus b dy plus cy equals 0, and treat this as if it were a polynomial and write this equation as a d squared plus b d plus c applied to y equals 0. In the case when this polynomial expression in D has distinct real roots, we can make use of the following algebraic fact. So if the polynomial operator has distinct real roots, we then use the following fact. We will consider D minus L, D minus K applied to Y, and D minus K, D minus L applied to Y. The first expression we see is D minus L, and then D applied to Y gives me Y prime, and K applied to Y gives me minus KY. Doing the differential operation again, we have D applied to the whole term in parentheses will give me Y double prime minus K Y prime, where here I need to use the fact that K is a constant. Since the derivative of K times Y, I can pull the constant out of the differentiation. Finally, I do L applied to this operation, and I have negative L Y prime plus L K Y. Doing a similar calculation below, we see that D minus K will be applied to Y prime minus LY. Doing the operation again, this will become Y double prime minus LY prime minus KY prime plus LKY. And now we observe that both of these expressions are the same. Hence, D minus K, D minus L is equal to D minus L, D minus K. In other words, the order in which I perform linear differential operators is irrelevant if the coefficients are constant. Let's see how this fact can help us solve a problem. Let's solve y double prime minus y prime minus 6y equals 0. To solve this problem, we will write the differential equation in symbolic differential operator notation. Our equation is equivalent to d squared, 2 derivatives, minus d, 1 derivative, minus 6 applied to y being equal to 0. Now, we know by the previous result that we can factor the differential operator on the left-hand side of the equation. And when we factor, we will have d minus 3, d plus 2 applied to y equals 0, Or, since I can flip the order of linear factors when there are distinct real roots, I can write this as d plus 2, d minus 3 applied to y equals 0. Now we recall the following fact from a previous lecture. This is the essential ODE. The essential ODE is y prime minus ky equals 0. We know how to solve this. This ODE has the solution y equals a constant c e to the k x, which we can now write in our notation as d minus k applied to y equals 0 is equivalent to y equals c e to the k x. Returning to our problem, we can now solve by using our essential ODE trick. If I take the first representation of my ODE and focus in on just the first term on the left-hand side, if I can make the first term on the left-hand side equal to 0, the d minus 3 applied to 0 will still be 0. I know how to make d plus 2 applied to y to be 0. I can make this 0 by choosing y equals c1 e to the negative 2x. Then I look at the second representation of my equation and realize that I can make this 0 by making d minus 3 applied to y equals 0. Using my fundamental or essential ODE again, I see I can do this by choosing y to be c2 e to the 3x. And to find the cumulative solution, I take a linear combination or add these two solutions together. So our solution will be y equals c1 e to the negative 2x plus c2 e to the 3x. So, by treating the differential equation as a polynomial differential operator and using factoring tricks, we're able to apply the essential ODE to solve our second-order constant coefficient differential equation with distinct real roots. Thank you very much.